Right.
So we want to go to this abstract idea. And I'm going to take it one level further in a second. Okay, but let's complete the inner product in function space. How am I going to truly do this inner product? What type of integral do I need? What other junk do I need?
Use it chronic or delta, seeing if they're...
I agree, at the end I'm going to have a chronic delta. But I want to now actually do this integral. How do you do this integral, this inner product in this function space? What's the dimensionality of this space?
The 2 dimensions.
It's two-dimensional space, right? So how many integrals am I going to need?
Two.
Two, I agree. Okay, Almar, go ahead. 0 to 2 pi for which one?
Azimuth.
The azimuthal angle, very good. So phi, right? Or phi.
Or phone.
Yeah.
Then is 0 to pi.
Then this is going to be 0 to pi. Okay, now what is my differential element going to look like in this space?
R sine theta d theta d phi.
So
Okay,
just sine theta, d theta, d phi.
so what do you think?
R sine theta d theta d phi.
Okay, so how many dimensions is that?
2.
The R gives you 3.
No, I didn't say dr.
Well, the total triple integral would be r squared dr is one sex
said
chunk,
r,
and
yeah.
then sine theta d
Yeah,
theta
r.
is the other, another, and
R
then
sine
just
theta d theta d phi.
Yeah.
R is attached to the...
But think about the dimensions too. Think about the dimensions then. So what are the dimensions of that space going to be? Or your differential element?
It would just be a
3 because it has R in it.
yeah, I'm going with no r.
There's no R. Alright? Because we're just talking about, it's called a solid angle space. Dale was working with this before, but it's just solid angle. It's per unit radian squared. Alright? So it's going to look like, this is equation number 433 in Griffiths. Okay, so we don't need the R, but what do we need still? We need all the angular parts of this differential
I
element.
thought the R and all that stuff was that what came from the theta aspect.
That will give you a length.
It was the d theta.
Yeah, so like RD theta gives you a little tiny length this way. This way.
R d theta, yeah, it's an arc length.
Yeah, an arc length.
That's one arc length.
It has units of meters.
Right.
And so then the other one goes.
goes.
Yeah, so we're talking about a area. It's called a solid angle,
All right.
and it's like so if you take a sphere of radius 1, what's the surface area of a sphere?
4/3
pi r cubed.
It is not 4/3 pi r cubed.
That's the
4
volume.
pi r squared.
That's the
4 pi
volume.
r squared.
Surface
Yeah.
area.
Oh, surface
There
area.
you go.
Four
Yeah,
pi r
so
squared.
So what is it?
It's a derivative of 4 pi r squared.
Yeah,
It's not the derivative of
that.
It's 4 pi r squared.
Yeah, it's a derivative of 4/3 pi r cubed. 4 pi r squared.
Is it really the derivative?
Yeah.
Why is it the derivative?
Because the volume is the area is the derivative of the volume.
All right. Got it. Yeah. All right, but it's 4 pi r squared. So if you take a unit sphere, all right, so it has a the radius of 1. What's the area?
4 pi.
4 pi. All right. And so that's kind of like that's the amount of spherical angle, the solid angle on the outside of that sphere. So if you took a little chunk of that, that sphere, a little bit of that solid angle, all right, it would come out in units of a certain percentage of 4 pi.
Is that like
And
Coulomb's
4 pi.
constant?
What's
1/4 pi?
1/4 pi?
Is that why Coulomb's constant is 1/4 pi? Because you get the spherical integral from Gauss's law?
Yes, yes, that's exactly, that comes in there, all right? All right, but this is solid angle, all all right?
So the
And so-
4 pi part is just the angle part, and then the r squared is just the...
That's exactly right. The 4 pi is the angle. So if you want to think about it like, you know, the angle that any sphere, the solid angle, how much it goes around of a sphere is always 4 pi. And then the area is just r squared times that solid angle. All right? All right. So what do I need to finish this? And it doesn't have the r's, but I still need the other parts.
Sine theta, d theta.
So I need sine theta, d theta, and
d theta.
d theta. Okay? Now, what is the delta function going to look like?
It's going to have L prime L and M prime M.
We can write it like this. Okay? Which is a statement of backing all the way up to that this is a normalized and complete basis set in function space. All right? So what we're going to eventually graduate to doing is instead of writing down this nasty integral, and by the way, for this nasty integral, what you would have to do? You would have to put in the explicit forms of these spherical harmonics.
Where the e's would actually want to cancel each other out, then because one's e to the plus and one's e to the minus.
Well, if that's for ML equals ML. ML prime equals ML. But if they're not, you can't cancel out no matter what.
Zero prime.
Yeah.
The delta function says they have to be the same or it
Well, yeah, but if you were to do an integral, it wouldn't, except for that case. So what we do is, I'll show you what we're going to do. We're going to create what's called a bra. All right, so this is L prime, ML prime. And then its goal in life is to find a ket, ML.
And that's our dot product.
So this is called a bra. And this is called a ket. And when I form a bra ket, what do you think a bra ket is the equivalent of?
Inner product.
An inner product in function space. And what do we know the answer to be? Equals this.
Same thing. It's just
All
a
right.
different way of writing that mess on the left.
Okay, now check this out. This is a big, huge deal. How often do you think it's going to come into our favor that we can write all these messy solutions out in this nice way where we don't have to work very hard?
I don't know, every time.
How about every time? Why?
Because the spherical harmonic is the same for everyone.
Okay, and back up. Where do the spherical harmonics come from? Schrodinger's normalizable equations, so square integral equations from
Those are
Schrodinger's
complete
equations
basis set.
by the method of
separation of variables.
separation of variables, because it's the separation of variables that gives us the complete basis set, right? So how nice. Our whole formalism is set up for us to eventually forget about doing a whole lot of nasty writing and to write it in terms of, you know, nice, I call these complex abstract vector spaces, but they're just an abstraction of the math that we're doing that makes our life a lot easier. Okay? So that was one point. I want to stress that today because we're moving actually back into chapter 3, and the whole goal of chapter 3 is to do this.
Right, because I peeked at chapter 3 and it was explaining these things as like vectors, or you could.
Yeah. So, but I figured this is a nice way. Besides this, what we're doing here, it's more of a continuation of 2. All right? But one thing I want to point out, is a bra necessarily the same construct as a ket?
No, because one of them would have. It would be like if you were to take, you know, like the probability of this of a wave function, you'd have to complex conjugate one side.
Very good. So already we're learning that what you do to make a bra is not just take the regular, you know, if this is the ket, y to the ln. To make the bra, you just can't use y to the ln. You got to follow the prescription that it has to be complex conjugated. So already bra is, you know, a ket essentially, but we need one extra step, and that's the complex conjugate. All right? We might have to do something more. Okay. So enough of that. Let's move on. All right. I'm gonna.
Now, do you just, in your back pocket, do you know all the spherical harmonics off your head?
No, not at all.
What will you just do? Come on.
Yeah. So here's what I know is like I know like
No.
y00, and the reason why I know y00 is because it's like the L equals 0, the projection of L equals 0. So the way I think of spherical harmonics in terms of the angular momentum that I do know for the hydrogen atom. All right, and so for an L equals 0, it's 0 angular momentum, and then the ML is the projection of that, which is 0, and so that's a sphere.
So that's,
So y00 is a sphere.
so, but yet that comes up to 1 over 4 pi to the 1/2.
Yeah, but if you look on the previous page, table 4.2, they show essentially the spherical part of it. So P00 is going to be, they show it right there in table 4.2.
Like a circle.
Yeah, well, it's a sphere. You got to plot it then for the azimuthal angle.
Yeah.
And then I think of the next one I know is like y to the L equals 1. All right, L equal 1 is an orbital angular momentum of 1. So what does that look like? In my head, I know it's a dumbbell. Right? It has the picture of the angular momentum. We're going to talk about this more. It looks like a dumbbell. All right, and then the MLs are the projection of the dumbbell. Right? So the dumbbell can be up, or it can be on its side, and it can be rotating one way or the other way. And so that will give you my projection. So that's what I know. But look, how often do you think you're actually going to have to go out and get those explicitly, except when you want a picture? Not very often.
Yeah.
Right? Because now we have this new machinery. And if we formulate everything in terms of these things, when we go to calculate our integrals, it's very easy. We get 1s or 0s. These guys are very clever at making their own life easier, right? Okay, so let me go on, if I can. Are you okay with that answer, Ron?
Yeah.
All right. So, let's go on. What we're next left to do is to solve f of r. F of r equals L times L plus 1. All right? And so that's where we find ourselves. And we find ourselves right here on the radial equation. And section, this is just called the radial equation. And it's section 4.1.3 in Griffiths. All right? So here's what we've got. If you go and you do that, and you plug in our original f of r right here, all right, what you end up getting is d dr times r squared dr dr. How about that? Minus 2m r squared over h bar squared. It's tough for me. It's tough if you're just writing this down and not looking, because I'm saying r and r. But there's a distinction between the capital R, the function of r. Remember? The capital R is equal to the r of r part. That's our function that we're looking for. Okay? Times v of r, and it's only a function of r, minus v times r equals L times L plus 1 times r. Oh, by the way, I needed an r over here somehow. Oh, I remember. And this f of r is 1 divided by capital R.
Yeah, it's 1
So
over.
then the next step you do this. You multiply it out.
I was
Okay.
stumped for like 5 minutes when I was doing that, and then I realized I was done.
Good. All right, but good. You struggled, right? And now today it's like, there you go. So guys, how many people work through this stuff? Okay, good. Congratulations. You got to work through it. That's how you're going to learn it. All right. So here's a trick. All right. So now this is a little bit cumbersome. It's cumbersome. So from experience, all right, no other explanation. Someone came up with a trick.
H5 squared down here.
A trick. All right. And the trick is to make